So when we're working with proportions, we're working with categorical data. Everything that we've done up to this point has been working with quantitative values that have a mean. We're going to see the same procedures, essentially, slight tweaks to the equations, but for right now we're concentrating on a single population, and within that population you're going to be surveying about a question of interest, and this is where you can get into a lot of like everyday statistics in terms of yes or no questions, to what extent do you agree, and your answer is a percentage or a proportion of that entire sample, and you're hoping that that is reflective of the entire population. So the significance tests that we are performing, looking at a confidence interval and a one sample z-test, those procedures are still essentially the same, just slight tweaks from working with means into working with proportions. Now, when we've been working with means, we've been emphasizing the difference between the populations notation and the samples notation. And we've had mu representing population mean, sigma representing population standard deviation, but those are more theoretical values. And what's more practical for us is to obtain a sample, and that sample has a mean x bar, and that sample's standard deviation is s. Well, when we're working with proportions, we still have this distinction between the population and the sample. The population's proportion, and this many people say yes, for example, this percentage says yes in the population, is just simply represented by p. Now when you're working with a samples proportion, we put a little caret symbol on top of that p, and we call it p hat. Now we're starting to see overuse of this letter p. There is a difference between p, p hat, and p value. Yes, they all represent proportions, percentages, probabilities, but they are proportions, percentages, probabilities of different things. Okay? P is that population's proportion. P hat is that sample's proportion that you're hoping is reflective of the population. P value we're still going to obtain at the end of our test. You know that represents a probability when the null hypothesis is true to get values this far away from what is expected. So P and P hat are just ratios. The total number of individuals goes in the denominator, and the number of successes or the characteristic of interest is in the numerator. So for P hat, that denominator, the number of people, is the sample size. And that numerator is just some value of x, the number of people who exhibit that trait. So much like we did with means, our rules are going to allow us to theoretically take a bunch of samples of the same size, and the distribution of those samples will become approximately normal. So a couple of key points here, conditions for using these rules. We need to have a simple random sample from a large population. It is important that we are trying to represent a large population here in order for these to be accurate. We already talked a little bit about p hat. We know that the mean of all of those p hats will become the population proportion p, and that is going at the center of this normally distributed set of sample data. The standard deviation step size is found using this equation right here. Square root of p times its complement divided by n. Now, p is always treated as a decimal less than 1. So let's say, for example, we had p as 72%, 0.72. Obviously, in this case, the complement, 1 minus p, would be 0.28. And those two values would be substituted in, and the sample size goes down in the denominator. Make sure you're following the order of operations when working this out. So to create a confidence interval for a population proportion, we are adapting this standard deviation equation. We don't know that population proportion p, so instead, like we saw with means, we're going to substitute in what we do know, our sample proportion, which is p hat. And that is going to give us our standard error measure for when we're finding a confidence interval. So, to find a confidence interval, the procedure is still the same. You're taking your p hat, your sample proportion, that goes at the center of the interval, plus or minus a z star value. Again, we're going back to the z procedures for this, no longer with t. So when you have a z procedure, remember the empirical rule takes place. If you want a 95% confidence interval, that's within 2 standard deviations of the mean, or that's approximately 1.96. 2 is the approximation. So if you want a little bit more precise results, go with the 1.96. There will be some questions where you're looking at a different level of confidence, 90% or 99%. I have those on our next slide here, and they're also linked on your homework assignment page. Once you have that z-star value in mind, you then multiply it by this standard error expression that we just discussed. Now, again, because these are z procedures rather than t procedures, we need to have a little bit more substantial sample size. We saw with t, we could get away with having a smaller sample. Okay, a couple days ago, we saw a sample that was just as small as 5. We can't have that with z procedures. We need more to it. So usually a good rule of thumb is that we need to have at least 15 successes and failures. So if you were to have a pure 50-50 split, that would mean that the minimum sample size for this would be 30. So keep that in mind as you're going through these procedures. Here are those common z-star values. Like I said, most often we'll be using 95%, but if it's not that, then it would probably be the 90% or 99%. Really, the 1 or 3 is just there because of the empirical rule for 68. Nobody's finding a 68% confidence interval. 99.7% sounds really good, but again, the sacrifice there is the width of the interval is extremely wide. It's not very practical and helpful. So let's take a look at an example problem here. This is from the textbook, and we're looking at the Canadian attitude towards guns. It says Canada has much stronger gun control laws than the United States, and Canadians support gun control more strongly than do Americans. A sample survey asked a random sample of 1,505 adult Canadians, do you agree or disagree that all firearms should be registered? Of the 1,505 people in the sample, 1,288 answered either agree strongly or agree somewhat. Before we get into parts A and B, let's establish our p-hat, our sample proportion. We know that our sample size is 1,505, and of those people, 1,288 agreed strongly or somewhat. So if we were to divide this out to get a rough decimal idea, we're looking at about 86%. Now, when you're working with that, obviously, the further out you take it, the more precise your answer is going to be. This is really about 0.8558. So we're going to acknowledge that we're going to have some inaccuracies with our final answer, especially because we're going to be doing further calculations with this rounded value. Once again, this might be an indication that we want to use technology rather than than do these calculations by hand. But let's move forward. Letter A, it says the survey dialed residential telephone numbers at random in all 10 Canadian provinces, omitting the sparsely populated northern territories. Based on what we know about sample surveys, what is likely to be the biggest weakness in this survey? Well, we're calling residential telephone numbers landlines. And we've talked about random digit dialing before, how it's biased towards older adults because they are more likely to have a residential phone line, a landline. We may not be reaching younger segments of the population, and maybe their opinions differ on this issue. So we're going to assume that we're okay to proceed into Part B. It says, nonetheless, act as if we have a simple random sample from adults in the Canadian provinces. Give a 95% confidence interval for the proportion who support registration of all firearms. Alright, so our 86% is going to go at the center of our interval, plus or minus our z-star value. We said 1.96. We're going to go as precise as possible. And we're going to multiply this by big square root. There's our p-value, our p-hat value, 1 minus 0.86. We'll just work that out. We're talking about 0.14. And divide by our sample size, 1505. When you have this all worked out, you're going to get a 95% confidence interval that ranges from 0.842 to 0.878 with some rounding. Again, so our interpretation, we are 95% confident that the true proportion of adult Canadians who feel strongly or somewhat agree that there should be a national registration for firearms in Canada, that proportion lies between 84.2% and 87.8%. Now, when we look at technology, it's pretty easy for our input. We need to provide our ratio, so our x and n value for p-hat, our level of confidence, obviously, and because it did not round, you'll notice that p-hat 0.8558, it's a little bit more precise, and our interval 83.8% to 87.3 or 0.4%, a little bit different than what we had derived by hand. This one proportion z interval, if you're looking that up on stat and tests on the calculator, this is letter A. So you scroll past all the numbers and it's the first lettered option. In GeoGebra, you're selecting a z estimate of a proportion. Again, same input, and we see our confidence interval boundaries down below. Now, when you're working with a set of data, you have an idea in mind of what you want that margin of error to be. So when you know that, plus or minus 3%, for example, you can work backwards to determine what the appropriate sample size would be in order to obtain that margin of error. So we see our back half of the confidence interval equation here. This is that margin of error. Well, to identify the sample size, we're going to bring n out of that equation. So, this is a little bit of algebraic work here, but it's doable. But it's done for us down here. We see n, the sample size, should be equal to z star, our level of confidence, divided by the margin of error. This is going to be a decimal. Okay, so for example, I had mentioned a 3% margin of error, so you would enter that as 0.03. That quantity is squared, and then we have yet again another variation of p. This is called p star. Now, p star is an estimate for what you feel that sample proportion will be. So if you go into this thinking that you have about 70% in that sample proportion, okay, you can enter 0.7. Okay? But the most conservative you can be, you're saying you have no clue, okay, go into this as 50-50. Okay, 50% success, 50% failure. Let that P star be 0.5. The complement's also going to be 0.5. That's going to give you the most freedom in selecting your margin of error. We have an example problem here about a local mayoral race in a large city with Gloria Chavez and Ronald Flynn. They're the candidates, and we're planning a sample survey to determine what percentage of registered voters intend to vote for Chavez. So we're going to collect a simple random sample of registered voters in the city. We are interested in the proportion P of Chavez voters with 95% confidence, margin of error no greater than 3%. How big of a sample do we need? So it goes on to say that even in the least contested elections, most of the time you're going to get between 30 and 70% of the vote for any given candidate. So we'll average those two out and just go with a P star value of 0.5. Again, that's the most conservative way to approach it. So down here we substitute these values into our equation. 1.96 from our 95% level of confidence. 0.03 as our margin of error. Divide those, square it, times 0.5 times 0.5. 1067.1. We're going to ignore the rules of rounding to make sure that we have at least a 3% margin of error. We're going to round that up to 1068. 1068 registered voters we would need to get a 3% or less margin of error. Lastly, for our significance test, remember, most recently we've been working with a null hypothesis when we're comparing two populations to each other. The null hypothesis has one mean equal to another mean. Well, we're going to go back to our one sample procedures where we were looking at a null value, and that null value is represented by P sub 0. So a lot of times in statistics, when we're doing these one proportion z-tests, we're going to go with 0.5 as our null value because we're interested in if we have a significant majority or minority. Is it significantly above 50%? Not always the case. It could be whatever is relevant to the question, but that would be inferred from the question itself. You can see our z-statistic calculation, and just a variation of our original z-score equation, which was x minus mu divided by standard deviation. Well, we're substituting in the relevant values here. Our value x is going to be p hat, our sample proportion. Subtract away our null value p sub 0, and then divide that by our measure of standard error. Notice that the null value goes in as the p value in the standard error here. And then our alternative hypothesis, that hasn't changed in terms of if it's one or two-sided. So an example here says that we talked about this in our probability unit. Newborn babies are more likely to be boys than girls, presumably to compensate for higher mortality among boys in early life. We want to test if this is actually true, and so we found a random sample, 13,173 boys among 25,468 firstborn children. So we'll make a ratio. There is our p hat proportion. We see it is a little bit over 50%, 0.5172, almost 52% male. Now we want to know if we really expected a 50-50 split. Is this convincing evidence, being almost 52% when we expected 50%, to say that yes, in fact, boys are more common than girls in the entire population? Well, our hypothesis here is that that proportion should be 50%, p equals 0.5. We suspect that it is bigger than that, so a one-sided alternative hypothesis, p is greater than 0.5. So to go about solving this by hand, we're substituting in our relevant values into our z-statistic equation. We see down here that we have our sample proportion p hat minus our null value 0.5, our standard error equation 0.5, 0.5. The null value in both of those gives us a z-statistic 5.49. We are 5.5 standard deviations away from what we expect at the center of this distribution. That's pretty far. And in fact, if we were to find this using our z-score chart, we can't do it because our z-score chart only goes out 3.5 standard deviations. So if you're doing this problem by hand, your conclusion here is that p is essentially 0, which is less than 0.05. Reject the null, accept the alternative hypothesis. We have very strong evidence that more than half of the firstborn children are boys. To use technology for this, we see our input and output screens on the graphing calculator. Again, you're providing the same information. The only thing new from the confidence interval is this null p-value and the direction of the alternative hypothesis. Be very careful down here when you get your output. We talked about this the other day. P-value 1.88 times 10 to the negative 8th power. This is a very small number in scientific notation. Do not say 1.88 is greater than 0.05 and that you fail to reject the null. In fact, as a decimal, this is like 1, 2, 3, 4, 5, 6, 7, and then you have your 188. An incredibly small number, essentially 0 like we said on the previous slide. Reject the null, accept the alternative. Okay. You can see the same things with GeoGebra right there. We're calling this a z-test of a proportion. Same input, same output. It's too small for GeoGebra, they just round it to 0 for our p-value. Last thing on the graphing calculator, when you are identifying the test, you want a one proportion z-test performed. So that one proportion z-test is option number 5 under stat and calculate. Okay? So try some of these problems with the homework assignment that is due Wednesday.